Good morning. This is Mike DeLaCluse with Lesman Instruments. Our clock is showing 9 o'clock, so we're going to go ahead and get started. I'm the president of Lesman, and I'd like to thank all of you for taking time out of your busy schedules to join us for air-fuel ratio, advanced air-fuel ratio control. It's going to be presented by Lesman's own combustion specialist, A.J. Piskor. This is the second in a series of presentations on combustion control. Today, A.J. is going to dive deeper into how fuel-air ratios can help maximize efficiencies in process heating equipment. They'll talk about some of the best practices, the do's and the don'ts, some techniques, and again, the best practices for air-fuel ratio control. A.J. joined Lesman earlier this year, actually early last year, as our combustion specialist, after spending 10 years with our manufacturing partner, Maxon, a Honeywell company, as a sales engineer. If he sounds a little depressed, it's because he's a devout Green Bay Packers fan. For those of you that are fans of other teams, please don't hold it against him, and I'm sure you can feel his pain. We will be muting the phone lines. If you have a question, there's a question tool built into the GoToWebinar toolbar. Please send me the question, and I'll make sure we get it answered. With that, I'm going to turn it over to A.J.
All right. Thanks for the intro, Mike, and thank you, everybody, for attending this morning. So as Mike covered today, we're going to do a review. Well, we'll do a brief review of the intro class. This is part 2 of our air-fuel ratio control, so I just want to go over some of the topics that we covered in the first class very briefly, and then we'll get into the maintenance to-dos and not-to-dos. And I also am going to go through and show you an example scenario of a burner. I'll provide a capacity, and we'll look up the information and then show you how I go through and put together a sheet that helps me determine the flows and the pressures required for that application. So again, just very briefly, just want to go over some of the combustion terminology that we covered in the last webinar. So first of all, stoichiometric ratio. This is the perfect amount of oxygen and fuel mixed during combustion such that nothing is left over. It's the value that's determined based on the calorific value of the fuel and essentially the density of the air, the amount of oxygen, if we're looking at volume flow, it's a function of the temperature and the pressure of the air. And I will go through and specify that in our example that I have a specific ratio set for our calculations. Excess air / lean is when we have more air that's present than necessary than it's required to combust the airflow, or combust the fuel rather. So this results in leftover oxygen. The example that I'll cover today is going to be with an application that has excess air and how changing the excess air affects the adjustment of the burner. Again, just want to cover that having the optimal air-fuel ratio can do a number of things for you. It'll prevent nuisance shutdowns. So if we have a burner that's running too rich or too lean, the flame detection device could give you a weak or no signal. So this will result, of course, in shutting down, requiring you to go through and repurge and light off your system again. So obviously we want to make sure that we have the proper air-fuel ratio so that we can prevent these shutdowns. Improving the fuel efficiency. So a lot of times when we've got applications, and we've got burners that we use for these applications, they're designed to operate at the specific air-fuel ratio because that gives us a good flame signature. And when I mean flame signature, I'm talking about the diameter and the length of the flame, as well as the discharge velocity out of the burner. And if we start burning too rich or too lean, that burner, although it may still be on and functioning, i.e. not shutting us down because of a loss in flame, you could be increasing your fuel consumption because you're either providing too much airflow into the system than what's required for the application, or if you're too rich and you have a furnace, for example, that requires the higher discharge velocity to stir up the chamber and get temperature uniformity, you'll have a lower discharge velocity running too rich. So again, each burner is different, each application is different. There's going to be a proper air-fuel ratio for that burner, for that application, and if we start straying from that, then we could be consuming additional fuel. We also have emissions-driven applications, whether it's an environmental or process-driven requirement. Again, the amount of air to fuel that you have going into the burner can increase or decrease your NOx or CO production, and also just help obtain better temperature control. So if we are off of our ratio for that application, for that burner, again, we could have a little bit more of a difficult time maintaining temperature control inside the system. I'm going to start getting into the maintenance to-dos and not to-dos and going over examples, but I first want to post a disclaimer on here that you should not adjust any of the air-fuel ratio control systems that you have unless you are familiar with the system as well as the safety components that tie into that system. And if at any point in time you are not comfortable with making these changes yourselves, and everybody's got a different familiarity with their equipment and with combustion, there are combustion service technicians that are available that are happy to go through and do this work. And if any of you feel like you need to get a service technician, please reach out to us and I can give you a referral depending upon what you're looking for and where you're located. Having said that, let's get into some of the maintenance to-dos and not to-dos. So first and foremost, and I think some of this is pretty straightforward, common sense, do use the proper testing equipment when adjusting the burner. So this would be the proper manometer or flow meter or orifice plate or combustion analyzer. We also want to make sure that the testing equipment that you're using is calibrated per the manufacturer's specifications. And we also want to verify the flow and pressure data with the burner manufacturer. Again, each burner is different. The manufacturer of the burner has cut sheets and data for the operating conditions for that burner, so flow and pressure for that burner, as well as a range of excess air that that burner should be set up for. So if you're going to go through and get into one of these applications, you'll definitely want to make sure that you get a hold of the burner manufacturer and make sure you have the most up-to-date and current literature so that you know what flows and pressures you need to achieve. Another do is that when you are making adjustments, you want to record values while making these adjustments in case if there's a condition that changes after you set the burner up and the burner's not performing as well, you'll have a record of where the values that you left off the last time that you set the burner off should be to see if any of those had changed over time. And also another big do is you want to make sure that there's some kind of a load on the system to take the heat away. A lot of times when you're adjusting these burners, you are in a, you're in an off condition, maybe you don't have process on and you're using the downtime to verify the air-fuel ratio adjustment. The danger is that a lot of these systems are set up based on a certain kind of heat load going through the system, so that you've got a certain amount of moisture inside of your dryer, and you've also got something to physically take the heat away. The burner, as you adjust it, is obviously going to be introducing heat to the system. You need to take that heat away, otherwise you'll start hitting your high temperature limits and shutting you down. So a lot of times this would just be essentially just going up and out the exhaust to make sure that you have the full flow rate into your system to pull that heat away, or if you have a process that it's not going to affect the quality of the product, or you've got an ability to dump or recycle the product, just something to take that heat away from the chamber. There was an application that I got into at one point in time where we didn't have the heat load, and even though you're below the temperature set point of the high temperature limit, the environment that the burner was firing into was a lot more dry because there was no product in there, and it caused a small grease fire at one of the recirculating fans. Unfortunately, I was working with a service technician that was keeping an eye on the system. We were able to put that fire out quickly, but it just shows the risk of setting this burner up by yourself and also without taking that heat away. So I want to make sure I emphasize that. You do want to try to adjust the burner under normal operating conditions. This is not always feasible or possible, but things like chamber pressure and temperature inside the system will adjust our pressure measurements and our flows going into the burner. And if you set it up under one condition, or if you're doing some kind of recycle, and then you switch over in process mode and you've got a vastly different chamber pressure, then all of the values that you had previously measured are going to be radically different, and I'll show you an example of this later on in our presentation. All right, let's get into the not-to-dos. So we do not, of course, want to jumper any safeties while adjusting the burner. All these safeties are in place so that we light the burners, we don't launch the burners, and we want to make sure that we keep these safeties intact when making adjustments. High and low gas pressure switches, I know that as you're adjusting the burner or maybe tuning the burner for the first time, you don't know where those should be set to, but you want to put those in place and not jumper around them because, of course, you're going to be physically lighting off the burner, and even though it's not production and it's going to be supervised, you're not going to always be able to detect right away if you have a regulator failure and you've got a lower high gas pressure switch alarm. So you want to have that set to a certain position, and then once you, if you're getting to the point where you need more fuel, then at that point then you can go into your pressure switch, just increase that setting as opposed to jumpering that out until you need it. You definitely want to not jumper any safeties and keep those all intact. You don't want to adjust the burner by eyesight only. Trained combustion technicians can tell you whether you have a rich flame or a lean flame just by sight. A lean flame, as I showed in the previous webinar, has a pale blue flame appearance, and a rich flame has a orange appearance, and the flame kind of it'll kind of rise up, and it'll have longer fingers that usually will extend out. This is a dangerous practice, just to adjust the burner by sight only. You know, at best you're going to get, you know, you could get pretty close, I suppose, but again, each application you want to verify that you have the proper setting by some kind of a tangible measurement, like the air flow, fuel flow, or if you're using it on a boiler or an indirect application, you can measure the oxygen percentage of the products of combustion. You know, eyesight's good. You want to be able to see what's going on, especially if you're having issues, but you don't want to base all of your air-fuel ratio adjustments by that by itself. For mechanical linkage and other air-fuel ratio control systems that have mechanical moving parts, a lot of them you'll need to change and make adjustments to those to hit your target values. And we just want to make sure that if you're going through and making any kind of changes to your air-fuel ratio, that you want to mark the linkage of where it was at originally. That way, if you have some kind of a change at some point, either during the burner tuning process or after the burner tuning process, or if the set collar on your linkage slips for some reason, you've got some kind of a mark, usually just a magic marker on the linkage arm will do the trick, or a piece of tape showing the location or making a measurement between two fixed points on the linkage will suffice. But we want to make sure that if you're going to change the linkage, you want to make a mark onto the linkage so you know where you started from. And again, just want to reiterate, if you're not familiar with the burner and you're not familiar with the system, just you don't want to touch anything or make adjustments to it, as I stated before in the disclaimer. So I want to go through an example of burner tuning and how I approach adjusting a burner. So I picked a burner. This is the Maxon Kinetizer LE burner. And in this application, the customer requires about 14 million BTUs per hour of net heat. And it's an emissions-driven application, and so we need to set the burner up for about 30% excess air. This is in an effort to control the NOx production for the burner. And we want to get as high of turn down as possible out of the burner. So the first thing that I want to just cover briefly when I look at a burner application, I'm usually basing it off a differential pressure. And when I look at a burner, I view a burner as essentially a fixed orifice. You've got air and fuel inlet, and let me preface this by saying this is with a nozzle mix burner or a port mix burner, where you have a separate inlet for air and for fuel, and that they mix internal to the burner, and then you'll have a common discharge coming out of the burner to the combustion chamber, specifically because you'll need to know the difference between the air and the fuel pressure entering the burner. If I view my burner as a fixed orifice, I've got my combustion air path and I got my fuel path, and the combustion air and the fuel mix after the quote-unquote fixed orifice. So for combustion air, this is in a mixing plate if we're looking at a line burner, or a mixing cone if we're looking at a nozzle mix burner that's externally mounted. There's going to be some kind of a cone or a circular plate, usually that has a number of holes inside of it to provide the right pattern of combustion air entering the burner block in the combustion chamber. Same goes for the fuel. There's either nozzles or gas ports, or a nozzle essentially is a collection of gas ports that will dictate the pattern of fuel that enters and interacts with that combustion air. The burners themselves are all fixed orifices in that the dynamic control portion of our air-fuel ratio is usually provided by control valves or ratio regulators or VFDs upstream of the burner. There's nothing that's physically changing with the shape of the burner, so we can essentially refer to it as a fixed orifice. And with a fixed orifice, if we know the net-free area essentially the design of the burner, and we know what the inlet and outlet pressure is across that burner, we can then infer what the flow rate through that burner is. And Maxon, for instance, installs test ports on the inlets of the burner, so that gives you a reference point for upstream of the orifice plate. And then the downstream measurement would take place inside the combustion chamber. So the back of the burner will have an air test port and a fuel test port. And then the combustion chamber, that would have to be provided externally or measured externally in some way, shape, or form, so that you've got your differential pressure across the burner. And again, the burner manufacturer's literature will provide us with the differential pressures and corresponding flow rates for the air and for the fuel, and so you want to reference that when you approach the burner and you want to make your adjustments. So in the example that I called out, we're looking at a Kinetizer burner from Maxon, and I pulled this directly off of their website. And we see that there are a number of different sizes ranging from 1.5 inch up to 16 inch. Again, my customer was looking for a burner that had a capacity of about 14 million. And if we look at the chart, we see that the 8-inch burner has a maximum capacity of 15.8. And the 6-inch, the one slightly, just below that, has only got a capacity of 9.8 million. So for our application, we'll want to take the 8-inch Kinetizer LE burner and underfire it to about 14 million. If we look at this chart, we also see some other crucial information that will help us set up the burner. So we see that we have a minimum capacity. It gives us our air flows at maximum and minimum capacity. It tells us what the pilot capacity and pressure should be, so that'll help us for adjusting the pilot. And then it'll also give us our pressure differential requirements for the combustion air and for the fuel. So on the 8-inch Kinetizer LE burner, we've got, again, the max capacity for the table is 15.8 million. The minimum capacity is 790,000 BTUs per hour. The airflow at the maximum flow rate is 3,280 SCFM. And the combustion air differential pressure, actually, I just noticed this looking at the chart. They give us two different values for combustion air differential pressure. They have air pressure at the inlet of 32 inches, and then the differential pressure is actually 27 inches. So I'll go through and I'll change the pressure values in my example to reflect the actual differential pressure requirement for the burner. And the natural gas differential pressure is at 40 inches water column, and that's for the maximum flow rate condition of 15.8 million BTUs per hour. So knowing that we've got these values, we need to reference the Orifice Equation in order for us to determine what the flows and the pressure should be at the intermediate firing rates. So the Orifice Equation relates the ratio of pressures to the square of the flow. So if we have a burner that has twice the, or if we have a condition where I need double the flow, it will result in 4 times the differential pressure for that burner. And when I'm going to pull up an Excel spreadsheet that I used when I was adjusting burners as not only as a reference to record the values, but also to help me determine what the differential pressure should be. I'm essentially either solving for flow or pressure in those two scenarios. So solving for pressure, P2, I just take the square of the ratios of the flows and multiply it by the reference pressure. And for Q, when I solve it the other way, I take the square root of the pressures and multiply it by the reference flow rate. So in the values that Maxon had provided in their table, I'm referencing those as P1 and Q1. So P1 is for gas, for instance, is my 40 inches water column. Q1 is my flow, which would be 15,800 SCFH of natural gas. And so those two values are known. And then I either know my pressure or I know my flow that I'm trying to achieve. So that just leaves the one unknown. So I've got my reference pressure and flow. I have a known pressure or known flow, and then I have to solve for the corresponding pressure or flow based on my unknown. So when approaching a burner like the Maxon Kinetizer LE burner, really there's a couple of different tools that you can use for measuring the differential pressure. So I'm sure a lot of you that are familiar with tuning burners and have adjusted your own burners probably have some of these in your toolkit. This is just a number of Dwyer manometers that we have that they have available. So some of them, and really there's a couple main differences between these. And it's based on the range of operation. So we look at the magnehelic in the bottom left that's got a range of 0 to 1 inch of water column. Our kinetizer LE burner has a gas pressure requirement of 40 inches water column. So of course, that particular magnehelix gauge is probably not going to be the best for this application. It might be good for measuring pressure at low flow, but it's certainly not going to cover the high end that we need. So you'll want to know what the burner differential pressures are at high fire, so that'll help you dictate which method of pressure measurement that you use. The good thing about the slack tube manometer in the middle and the incline manometer on the left side is that they're using a fluid inside of there. And the fluid is great because it essentially will zero itself, or it's very easy to zero those manometers, versus a digital manometer. It does have a zero on it as well, so you can zero that and you can change the zero set point. But as far as a calibration standpoint, you'll want to make sure that if you are using a digital manometer that they are, again, calibrated. A slack tube or an incline manometer requires little calibration except for maybe adding some additional fluid inside of the manometers itself if you lose some. Another tool that you would want to use, especially with this emissions-driven application, would be a combustion analyzer, something that would go through and would tell us what the NOx and the CO levels are coming out of the process. It also gives you an O2 reference so that you can correct for oxygen levels. And these analyzers are also very handy when adjusting indirect fire applications like boilers or heat treat, radiant tube burners, where you only got the products of combustion to measure, because having an O2 measurement essentially tells you what the air-fuel ratio would be for that system. So you still want to go through and have some kind of a flow verification, but having this analyzer downstream will just verify that the flow ratings are correct and that you're getting good combustion. I'm going to switch now to my example, and what everybody should see now, and I'll allow for time for a little bit of lag, is I have a table set up in Microsoft Excel, and I'm doing an example here showing mechanical linkage. So this would be the Maxon microratio valve. I'm getting cut off here. Okay. Oh, that's okay. I'll move over there. So a Maxon mechanically linked microratio valve, you can go through and it's got a screw carrier assembly that allows you to fine-tune your gas. So there's essentially 12 different index points if we look at column A. And you'll see that there'll be tick marks next to the screws on the screw carrier assembly that indicate minimum fire, and then there's index 1 through 10 going up to maximum. And actually, I have this reversed. My firing rate percentage should be the other way. Change that real quick. Yeah. Oops. That's close enough. So you guys understand that the minimum is going to be at 0%, maximum is going to be 100%, and then we can kind of interpolate from there what the individual firing rates will be. But when you're setting up when you have a mechanical linked system, you've got all that gas adjustment, but the air valve on that, I only have 2 points of adjustment. I can only set the air valve at the minimum position and the maximum position. Just the way that that system is set up, there's not an individual screw carrier assembly on that air valve. It's a hard mechanical linkage. And there are 2 adjustment set points, so I can go through and I can set the air valve wherever I want it at minimum and at maximum just by adjusting that linkage. But I'm essentially fixed there. So when I start looking at target values, so target values are essentially before I set the burner up, I'm going to dictate what my air pressure should be at high fire and low fire based on the operating conditions that I want for that burner. So by operating conditions, we're referring to the maximum capacity, or the capacity rather, at each index point, as well as the excess air percentage. So we said that at high fire, so at index maximum, I need the capacity to be 14 million BTUs per hour and 30% excess air. So if I scroll over to here, I can then determine, because I know what the flow should be, I can then calculate what the flow should be based on the formula that's shown up in the formula bar. So I'm taking the capacity multiplied by 1,000. That gives me the essentially the gas flow, and then I'm multiplying it by the amount of excess air that I would need, and then I'm multiplying it by the stoichiometric ratio of 9.6. And that's a stoichiometric ratio that Maxon uses commonly in their literature based on an assumption of combustion air temperature and essentially density. Usually it's at I think 60 or 70 degrees Fahrenheit. If you are preheating combustion air and you'll have a higher temperature, you're going to want to change the stoichiometric ratio accordingly because the differential pressure that you measure is not going to translate to the same volume flow as it would in regular 60 or 70 degree air. So you can go through and adjust that, and you can set up a dynamic spreadsheet here in Excel that can help you, and you would just change the stoichiometric ratio accordingly based on the new temperature that you're measuring. So I don't want to go through that example right now, but just want to specify out that we're multiplying by 9.6, and that's what our stoichiometric ratio will be for this example. I take that divided by 60 to get my airflow in CFM, which matches the catalog rating. They specify their airflow in CFM. And then from here, I go through and use my Orifice equation. So now that I've determined the capacity and the excess air, I can then calculate my airflow. So my airflow, which would be Q2, is known. And then I use the equation where I'm solving for pressure with a known flow to get what my air differential pressure should be for that flow rate. And then I do the same thing for my gas differential pressure because I know what the capacity is, I know what the fuel consumption will be, and then from there I can now go and solve for gas pressure. So before I made the wrong assumption of 32 inches, so I can go through and change this to be 27 inches, and I'll change it up here as well. And that actually gives me my updated air differential pressure. So now I've got everything that I need to go through and set the burner up. So again, with the mechanical link system, I want to set my air pressures first. So I'm taking my mechanical linkage, and this is while the burner is off. So I have no gas flow, but I have combustion air blower on and all the other system fans on. I can then go through and I can measure my air differential pressure, and I can go through and set the linkage on my mechanical link microratio valve so that I got my air pressure at high fire and low fire. And then what I have here, and again, we'll just assume for now, and I'll have to go through and change this slightly. Apologize for me editing out my spreadsheet here in real time. I'll just leave that for now. So what I did was I just changed my reference pressure to reference the 27 inches of water column needed. So, and if I do 21.3 inches at high fire, there's going to be, and I'm going to delete these out for now. So when I go through and I measure the air differential pressure for this application, it's going to gradually increase up, but it's not going to be increasing in any kind of a linear pattern. You think about my air damper, it's a butterfly valve. It's going to exhibit the flow characteristics of a butterfly valve. So it may be something like 0.5, 0.9, 1, 0.6, and then I'll just jump up from there, 3, 6, 9, 12, 15, 18, 20. So I don't know what those values are, and in fact, you won't know until you actually turn the burner on and then just measure what that air differential pressure is at these individual index points over here on the far side. So the air essentially is going to be fixed because I can't change my low or high fire without affecting the rest of these points. So my air pressure is fixed. Now what I have to do is I have to match the gas pressure such that I get the targeted amount of excess air that I need. So here at the far column, I've got my excess air, and this is based on the air pressure as measured in my gas pressure. I can adjust each index point. I can adjust my gas pressure because I have adjustment screws on each of those. So I can actually turn these up and down as needed to get around 30% excess air. So looks like we're okay here on the far side. But then what I can do is if I'm a little low on excess air here at this index, I can then increase my gas pressure. Or I'm sorry, decrease it rather. And I get about 30, you can see that value updated to about 30%. And I can adjust these out as needed to hit hit 30. There we go. So it's a little trial and error, but then you can go through and, of course, the gas differential pressure that you measure is going to be a function of the accuracy of your manometer. So that's why I do 0.1 inches. And if you guys have used a digital manometer, you know that they jump around all over the place when you're trying to operate. So I kind of take a running average, and if it's jumping between 13.2, 13.4, 13.1, 13.5, then I know that I've got my gas set okay because that all kind of averages out to 13.3. I'll just keep on going down here and adjust my gas pressures accordingly. And as you get closer to the low end, the excess air, you're going to start tapering that up a little bit. And that is because it's going to be very difficult to try to control this burner and tune it out to get 30% excess air because we're already at 0.1 inches water column and 0.2 inches of water column on our gas and our air respectively. So to try to hit that is going to be a tough task. But you also, it's not necessarily such a bad thing to have excess air at the low end. This emissions-driven application, usually the way that these are drafted up, you need to show that you are efficient over maybe a 4-to-1 turn down. So we're only looking at above index 2 or index 3. And the other good thing is that even though maybe we're not as efficient from a fuel standpoint, we're able to go through and drive the combustion chamber down to a lower temperature with additional excess air. And really, when your burner's at low fire, that's what you want. You want to drive your temperature down on your chamber. So let me just go back through here and, oops. I'm going to go the other way, rather. Okay. So then I'm just taking my air pressure as measured and adjusting what my target gas pressure should be so that I get around 30% excess air. Maybe I'll start tapering up a little bit more, and maybe I'll split the difference there. Okay. Oh, wait, let me go. Okay. So So now I've got my air differential pressures, I've got my gas differential pressures, so now it's just a practice of going up and at each index point verifying my air differential pressure and my gas differential pressure, and then changing those so that I get my target excess air. And you may notice that the air differential pressure may change slightly when the burner's on versus when the burner's off. So if that's the case, you can go through then and just change the value here in this column and then use that for your new corresponding gas pressure. And again, excess air should never go up as capacity increases. We want to make sure that it's either laying flat, especially in this application where it's emissions driven and I need to have 30% excess air, or it's gradually just tapering down, kind of like what we have here, where we start with a high amount of excess air at minimum, and then we start gradually going down towards 30. If you start increasing your excess air at high fire, then you're taking away that available heat, and if it's extreme enough, you can actually start cooling your chamber down as you increase firing rate. And of course, your temperature controller is going to say, well, my temperature is going down, I need to increase my firing rate even more, and then of course now you're enhancing the issue at hand. That's why we always want to be mindful of our excess air percentage. If we take a look at the curve and what this looks like, and it looks floppy on purpose, is that I've got a little bit of a hump. It kind of levels off, then it peaks off, and then it levels off again. Again, because I don't have control of the airflow at the individual firing rates, it's essentially whatever it is, and I just have to match my gas to the air. So although it looks somewhat linear, there is some curvature to it. And now we'll switch gears, and I'll talk a little bit about parallel positioning. So in the previous presentation, I talked about the different methods and essentially going up in tiers of control. So beyond mechanical linkage would be parallel positioning. So the main difference is that they're both air and fuel butterfly valves, but now I have a little bit more control over the characterization of my air valve. And this actually gives us quite a bit of flexibility when we start looking at the application and start looking at a target value of where we need to set up the burner. So now that I have control of my airflow, I can now dictate what my capacity should be, not just at low fire and high fire, but all those other individual points. I couldn't do that before with the mechanical link system because my airflow is fixed. There's no adjustment, but now I've got adjustment, and what I can do now is I can specify, hey, as I have equal increments in firing rate or indexes, I can move up equally in capacity. So this will give me, and I'll show you the curve after I'm done on this page, it'll give me a nice linear curve, which means that for every increment in firing rate, I'm achieving the same capacity increase regardless of where this curve falls on the, whether we're at the low end of the curve or at the high end of the curve. Again, I've got 30% excess air, and now I can go through and dictate what all of my airflow should be at each index point and what my corresponding differential pressure should be on that air. Just in an effort to save time and confusion, I'll just keep the flow rate, the differential pressure the same as 32 inches is what I originally had assumed. So now I can, before I set the burner up, I already know what my air and my gas pressure should be at each index point for the entire range of the curve. So now it's just a question of setting that up. A lot of times I like to set up the air with the burner off at first. That gives me a good baseline. And then when I turn the burner on, I can now adjust the air and the gas in real time as needed to match the curve. And again, we see that, what I did here, and let me move over a little bit, is I have the same air and gas pressure settings, or they're going to be pretty close. Again, I decreased the gas here just to give me a little bit of a taper on my excess air. I'm going to taper gradually up when I'm at low fire, and then I'll go down, and then I'll hit the 30%, just a few index points in. So those values are going to be slightly different. These are the corresponding capacities for those values. And now that I have so this system is another Maxon control system called their Smartlink MRV. And at each index point, which is the equivalent of a screw carrier on our mechanical linkage, I can now display what the air valve and the gas valve position are. And again, I want to record everything, so I want to not only record my air and gas differential pressure, I want to record what my air and gas valve positions are. So if we look at our curve, we go through and set everything up, and we look at our curve, here's our nice linear curve. So between index 0 and 9, we start at our low capacity, and then we ramp right up to our high capacity. And we see a nice linear curve compared to the other curve that we show with the mechanical linkage. So, instant value with parallel positioning is that now I can have a really nice linear, well-defined curve versus the mechanical linkage where I don't have that flexibility. I can now also display what my valve curves look like. So I just plotted the combustion air curve and the natural gas curve, and this will give me some good information as far as I can relate these to the flows or the pressures on those lines, so that if I ever need to change my excess air percentage, I can go through and I can essentially just take the data that I have based on the valve curves and the related pressures and flows, and then I can go through and come up with an alternate curve that would be somewhat close. Then, of course, I can verify that by physically setting up the burner and ramping it up and down. So this is another huge benefit of the parallel positioning, is that I've got a record of the valve positions, and I can relate that to flow or pressure. Just one other quick example. I know we're running short on time here. When we look at a system and we set it up based on certain conditions, and then after we start running production or changing damper positions, we see that there's a change in the chamber pressure. We want to see what that looks like or how that affects our air-fuel ratio. And now I just did a very modest change in differential pressure. I only did about 1 inch of water column. And we see that our air pressure, or our excess air percentage, actually goes up. And our curve, if I compare the old curve to the new curve, it's still pretty linear. There's a slight curve to it, but it all jumps up. Because I have an extra inch of suction in my chamber, it's going to be pulling additional airflow and fuel flow through the burner, so everything's going to jump up. But the good news is that with this particular burner, the air and the fuel differential pressure requirements are pretty close, so it'll affect each the air and the fuel equally. If you've got a burner that has a very high air differential pressure and a very low gas differential pressure, obviously a change in combustion chamber is going to be that much more critical to maintaining your air-fuel ratio, because now you've got a much higher gas flow going through if you have an extra suction in your chamber, and that's going to really throw your air-fuel ratio out of whack. So just all the more all the more reason to mind your air-fuel ratio and your chamber pressures and when you're adjusting your burner. So having said that, that's where that will complete my portion of the presentation. I appreciate your attention. And Mike, do we have any questions online?
We do not have any questions. So if you have a question, now would be the time to type it into the GoToMeeting tool. Well, we do have our first question.
Now, just to remind you, of course, I've got my contact information available. Please reach out to me if you think of anything else, or if you are looking for some kind of a service technician to help you out with this, I can give you some kind of recommendations.
All right, here's our first question. Let's see if you can answer it, AJ.
Okay.
Adjusting the burner while monitoring flame temperature or burner refractory temperature is a decent method of achieving maximum heat. However, what's a good way to measure maximum heat transfer from the burner? For example, increasing excess air might cool the flame, at the same time increasing the heat exchange rate within the process. Is there a tool to measure true maximum flame energy, including heat transfer rate?
That's a great question, and there's not one that comes to mind, but let me do some research. We've got the contact information for the person that asked the question. So who is it? Eric. Eric, so Eric, let me do some research into that, and I'll get back to you. But great question.
Any other questions, please feel free to type it into the tool, and we'll get them answered. If for some reason you have a question after this session, please feel free to contact AJ. AJ's email is right there. It's very simply ajp@lesman.com. So feel free to contact him.
Also would appreciate any kind of feedback if you guys have any other topics. I know I didn't cover every single air-fuel ratio control system, but if there's something that you wanted me to cover for a future webinar or anything else that you think that we should be sharing with you, please reach out to me. I'm always looking for additional ideas, whether they're air-fuel ratio control or other combustion topics. We'd be happy to hear from you.
At this point, I don't have any other questions. So, AJ, thank you very much for your presentation. Our next webinar is going to be February 10th, and it will be presented by Tim Bulbuck of Siemens. Tim is the level expert in our area, and the topic is going to be level applications in a hygienic environment, specifically some new radar product that Siemens has come out with to fit that application, which is very unique, and as far as we can tell, there isn't anything else like it on the market. You can either sign up in the training center at lesman.com or wait for the announcement to come out, which will come shortly. At this point, I don't have any other further questions, so our presentation will conclude. Thank you all very much for attending. The recording of this session will be put up in the next couple of days, so if you have associates that want to view it or